What's going on, you guys? So today we're going to do the Divisor game. So the idea behind this one is, I'll just read it for you. So Alice and Bob take turns playing a game with Alice starting first. Initially there is a number n on the chalkboard. On each player's turn, that player makes a move consisting of choosing any x with x within 0 and n, and the remainder of dividing n by x is 0. Then they replace the number n on the chalkboard with n minus x. Also, if a player cannot make a move, they lose the game. Return true if and only if Alice wins the game, assuming both players play optimally. Okay, so let's do some examples so we can get a feel for what's going on here. So let's say n equals 1. And Alice goes first. So Alice cannot make a move, right? Because there are no numbers between 0 and 1. So Alice loses. False. Let's see, n equals 2. So Alice can choose 1. So if Alice chooses 1, so let's do this this way. So 1, Alice loses. 2, she can subtract 1 from 2 and write 1 on the chalkboard. And then Bob is faced with 1, and then he loses. So she wins. So we'll return true. 3. So Alice can choose either 1 and, so 1 is her only choice. So she has to subtract 1. She writes 2 on the chalkboard. And now Bob is going to choose 1, and then Alice has 1, and then she will lose. So this is false. Let's do one more. So let's see. So 4. So Alice can choose 1 or 2. If she chooses 1, she'll have 3. She'll write 3 on the chalkboard. So there's 2 options here. She can choose 1 or 2. So let's see what happens on each of them. So if she chooses 1, then she's going to write 3 on the chalkboard. Now Bob has to choose 1, so he writes 2. And now Alice can choose 1, and now Bob has 1 and he loses. Okay. Now what if Alice chooses 2? Okay, so Alice is going to choose 2. So she subtracts 2 and leaves 2 on the board. Bob can choose 1. Now Alice has 1 and she loses. False. True. So Alice is not going to choose 2. She's going to choose 1. So it's starting to look like even numbers she can win, false numbers she loses. Whoever gets 1, basically whoever gets 1 is the loser. So who's the person that gets stuck with 1? So let's just take a look at 5. Okay, 5. So Alice, her only choice is 1. So she writes 4 on the chalkboard. Bob chooses 1. Bob is going to follow this playbook right here. Bob chooses 1. So he writes 3 on the chalkboard. Alice has to choose 1. So she writes 2. Bob chooses 1. Now Alice is left with 1 and loses. Okay. Okay. So for any given number n, let's think about this. For any x in 0 to n, if n modulus x is 0 and so let's think about this. So if Alice chooses 1, that is a valid choice. she's giving Bob the option to play the game starting at 4. And so Bob is going to be able to win because he's going to leave Alice with 1. So if the previous game is a winner, if the previous game is true, then Alice is going to lose. If the previous game is false, then Alice is going to win. Okay. So if it's a valid choice of X and the previous game is false, then she's going to win. Right? You see how we build up like that? So if Alice chooses 1, she's going to lose because this gives Bob a winning opportunity. Okay, so if n is 4, Alice chooses 1, then she's going to win because the previous game is a loser. And she's basically giving Bob the starting at 3 game. Okay, cool. So here's this is our brute force solution. We'll return true. And then if we get through all those and we don't find a true, we return false. This is brute force. So it's going to be, let's think about time and space complexity. So it's n times for each n there's many calls to Divisor Game which take a long time. Yeah, this looks to be exponential, I think. I'm guessing this is like 2 to the n. And then space complexity is going to be n, because we're going to have to call. So if we have to call 0 to n minus 1, we have to call Divisor Game 1 to n minus 1 times. So there's going to be n calls of Divisor Game on the call stack. Man, let's think about so for each loop, we call Divisor Game. And what's our base case? So if n equals 1, return false. Okay. So for every x between 1, so for every number between 1 and x, there's that many nested for loops. Wait. Is this n to the n? Time complexity. Yeah, so it's a pretty this isn't going to work very well for large n. But let's just see if we can get it to work for some small n. So if n equals 1, return false. For I in let's call this x to keep it consistent with the description. So if it's is a valid divisor and the previous one is a loser, wait, let's think about this. Is this n or is this x? No, this is n. So we're checking all the numbers between 1 and n to see if it's A, a valid divisor, and B, n minus x. Wait, n minus. So there were two options. I'm trying to think of like what happens when there's more than one option. So if Alice chooses 2, this is 2. It's n minus x, right? See, if n is 4 and Alice chooses 2. Wait. Now it's 1. So if we do 1, then we're going to make sure we check all the previous values to see. Alright, so we can run this for some low values. Let's do like 5. So as n gets bigger, the time to run it is going to exponentially increase. Okay. $152 milliseconds. Let's look at 5. Let's look at 20. Well, no, let's just do 5. So it took 152 milliseconds for 10. Let's see what it takes for 5. Oh, it takes longer. Interesting. That's just it's kind of a quirk with using LeetCode servers. Okay, so let's see if we can do better. The first easy win is to just add a memo, or to add memoization. So we could use a map. We could say it's a mutable map of, it's going to be int and boolean. And so we could say if memo n does not equal null, return memo n. Otherwise, we gotta add the new value to the memo. let's see if that works. Nope. Time limit exceeded. What's the problem here? Let's think about this. What is the issue? Okay, let's try and think of what the issue is here. Let's see if we can figure out what's going on here. Memo. Oops. So let's do this little print line. All right, let's try that. Oh, so we're only adding the true values. Oh, I see the issue here. Okay. So let's add the false. So memo and okay. So let's try that. Huh. Interesting error here. 3 should be false. Interesting. So adding memo of x equals false in here is incorrect. And why is that? Okay, so we've added a memoization here, so that speeds things up a little bit. And so that should just be O of n runtime because we're only going to calculate memo, each value of memo once rather than multiple times. But we still have O of n space complexity because of the repeated calls to Divisor Game. So let's think about, so we've done like a top-down approach. Now let's think about doing a bottom-up. Okay. How can we do bottom-up? So we know memo of 1 is going to be false, right? Because if you get 1, you have no shot. If you have memo 2, you're going to win. That's true. So now we can say for x in 3 until n, we can say memo of x equals, so we know that n modulus 1 is always going to be 0. So that's 1 is always going to be a valid choice. So if we have 3, we can always write down 2. Right? Okay, so if we're always choosing 1 in this case, then memo of each additional value is just going to be not the previous value. Right? Because our initial condition was if Divisor Game of n minus 1 is a loser, right? Then the current game is going to be a winner. Now I believe this was n minus x. It wasn't n minus 1. That was an issue there. But in this case, so if we have 3, the previous one is a winner, so 3 is going to be a loser. If we have 4, the previous one is a loser, so 4 is going to be a winner. And then at the end, we're just going to return memo of n, the last value. Oh. In Kotlin, we need to make sure that we're handling null checks. Oh, oops, that's supposed to be x. Oops, another null check. Okay, there you go. So that takes up a little bit less space. As you can see here, the memory went down a little bit. That's because we're reducing the stack frame from n calls on the stack frame to just 1 call. And it's still O of n time complexity because we have to calculate from 1 to n. And there's one more. We could get rid of the map data structure as well. As you can see, we're only using the previous 2 values. In fact, we're only using the previous value. Yeah, so we're just using one previous value, right? Because the next value is just the opposite of the previous value. Okay, so let's see if we can get rid of the memo. So var, so if no, we don't need that. So var previous equals false, right? That's for, so if n equals 1, are we going to turn just previous? For x in 2 to n. Var temp. So we're just flipping it back and forth every time. Does this work? Let's think about 3. 1. So it should return false. 2. Should return true. Let's see if this works. Okay. Yeah, so that works. So we're just using the previous 1 value. So we're able to get rid of the map data structure, and so that now we have constant space and O of n time for this solution here. And like if you checked out the discussion, they did some interesting. There's some interesting talk about proving that actually if n's divisible by 2, then you're always going to win, because you can just subtract by 1 and give the next person a loser. And so this is the fastest yet. If you're interested in that proof, go ahead and check out the discussion section. But yeah, so we started off with just the basic recursive solution, and that was exponential time and O of n space. Then we added a hash map to avoid calculating the same value more than once. Then we got rid of the hash map by just noting that we only need the previous 1 value, and we're just flipping it from true to false every time. And so that final optimization gave us O of n time complexity and O of 1 space complexity, because we're only storing that 1 value. All right, you guys, that has been Divisor Game. And this is an example of dynamic programming. This is a tougher concept, but it's really fun once you start getting the hang of it. All right, look out for more of those. See ya.